Right, I wanted to share with you guys a new graphing and fitting program that I've been working on. Um, so to do that, I'm going to look at some student data for a lab we did last semester. So this lab, we measured the capacitance of a parallel plate capacitor and checked the capacitance at different distances, different gaps between the plates. So I like to title my labs like this: How does the capacitance of a parallel plate capacitor depend on the distance between the plates? It's sort of asking a question that can be answered by making a graph. For this lab, we used the Pasco parallel plate um, apparatus. It consists of two 7-inch diameter plates that can be slid back and forth to change the gap. And we also used a relatively cheap capacitance probe. So you can sort of see the setup here. When we connect the capacitance probe to the plates, we can measure the capacitance in picofarads. And the students collected data for a bunch of different gaps between the plates, and they measured the capacitance for each one of those gaps. So then they're supposed to graph the data, which is what we come to here. Now, last semester I used Pivot Interactive, which is a Vernier product, but it's an online product that you have to pay for. It costs, I think, $15 per student per semester, and I've been paying that out of lab fees. But if I don't have to pay, I'd rather not. But I use it almost exclusively for the graphing capability. Pivot Interactive has lots of other stuff, but it's the best graphing tool that I've found for students until now. And what I like about it is that it's relatively easy to use. It lets you put in error bars for both X and Y. It does curve fitting, makes relatively pretty graphs, and when it fits the curves, it gives you the uncertainty in the fit parameters. So those are all really cool features. The things I don't like is that it only has a finite number of curves you can use. You can't pick an arbitrary curve to fit to your data. And the cost. That's the other thing I really don't like. So, plus there were some other features I wanted. So I created a graphing program, and I've placed it on the network drive. So if you go to the departments and physics and scroll down, you will find a file called graphing and fitting ung.zip. And if you unzip that file, I've already done that. I put it on my desktop, I unzipped it, and this is what you'll see. So the two important things are an example data file and the actual executable. Now, because I've already done this, I went ahead and put my student data inside this example data file. So here is the student data, and this was the data that the students collected. And so there are a couple things here. The first thing is the first row is special, and these data files have to be formatted perfectly for my program to read them. So the first row is special. This is the X label. So capacitor gap in this case. This is the X unit, meters. This is the Y label, capacitance, and this is the Y unit, picofarads. Okay, and then each row represents a data point. The X data, in this case 0.1 means 10 centimeters, so 10 centimeter gap, and the X uncertainty. And actually, because we measured these with a ruler that had millimeter markings, I'm going to assume that the X uncertainties, were 0.5 millimeter. Now, long discussion about how you decide what your uncertainties are when you're taking measurements, but that's what we got. That's what I decided for this, and that's just because we were using a built-in ruler on the capacitance apparatus that had millimeter markings. Okay, So the next thing I needed was the capacitances, so I got those from the student data. And then I need the uncertainty in the capacitance. And what we found looking at the manual was that this particular capacitance probe has an uncertainty of 0.6% of the reading plus 0.2 picofarads. So to input that into my spreadsheet, I used a formula. I said, okay, that is equal to the capacitance that we measured times 0.006, 0.6% plus 0.2 microfarads, and that gave me a uncertainty for each data point. Okay, so there's our data, and let me go ahead and close that out because, like I said, I already put that data into the data file. All right, so let's open up the program. Okay, and here we have the program that I wrote for graphing student data. All right, so there are some instructions here, but I'm just going to go over it. So there are two ways to get data into this program. One way is just to type it in. Like I could just literally type in, all right, I want my X label to be gap measured in meters, and my X values are 0.1, comma, 0.08, comma, 0.06, right? Go on and type those all in. My X uncertainties are 0.0005, comma, 0.0005, comma, right? And type those all in. That works. Or if I load the data file, I can populate that automatically, and it will basically just type in all the data for me. Now it's still sitting here in these boxes, and what's in these boxes is what counts. So if I want to go in and change something, I can. Oh, I see. In fact, I do want to, because I've still got 2 millimeters as my X uncertainties, and I actually want these to be 0.5 millimeter each. So without going through and changing the data file, I can change what the program is going to actually graph by going in and changing these values in the fields here. Okay. Also, for whatever reason, it put a period between capacitor and gap for the X label, and in fact, maybe I just want to use gap for the X label, right? Okay, so once I've got all this looking the way I want it to, either by typing it in by hand or by loading it from a file, I press load data, and it creates a data table over here. And that data table is what the computer's actually going to use to do the graphing, and we just want to check to make sure it parsed everything correctly and everything looks right. I think it does. And then we get to put in our graph options. So this is going to be capacitance versus gap. I'm going to go ahead and start X at 0. X maximum, let's see, the maximum data point is 0.1, so I'm going to make the graph go up to 0.12. Minimum Y is 0. Maximum Y, the biggest capacitance was 27, so let's go to 30. Okay, and then we get into the fit parameters. Now, according to the theory that we have, the capacitance is supposed to be equal to epsilon 0 times pi r squared divided by the gap. And that gap, of course, is our X, right? So this is effectively just this whole, the epsilon 0 and pi and r, those are all constants. So this whole thing could be thought of as just some constant divided by X. So that's what I'm going to use for my fit. And that fit only has one parameter. So I'm going to tell it we only have one parameter. And I'm going to type in my fit function, a over x. Now, I don't type in y equals a over x. I just type in a over x, where a is a fit parameter that the computer is going to pick the best possible value, and x is my independent variable, in this case the gaps. And I can pick a starting value, and I'll go ahead and show that. If I do a manual fit with a starting value of 1, what you can see is that it's a terrible fit. And I could do this manually. I say, okay, well, what if I used 0.5? And I do a manual fit, and that got closer. And maybe I want to try 0.3, okay, and that got even closer. And so you can do manual fits, which I really like. I love the idea that I can type in the values that I want to type and see what kind of curve I get and see how it fits. Or I can click auto fit and the computer will find the best possible value of A to fit my data. And what I hope you see right away is that it's not a good fit. So we can just tell just by looking at this that that's not a good fit. Oh, by the way, there are error bars on those data points. They're just so small they're hard to see. We'll talk more about that in a little bit, I think. But here, what's really interesting is the curve's not a good fit. And that's because this is student data, and there were some systematic errors in the data collection. So I'm actually going to account for that in my model. And I'm going to say, okay, we're actually going to use 3 fit parameters, not just 1. And instead of dividing by x, I'm going to divide by x plus b, where b represents a systematic measuring error in the gap, okay? And then I can also do plus c, where c represents a systematic measuring error in the capacitance. Now it's really important, if I'm going to use 3 fit parameters, a, b, and c, in my function, I have to tell the program I'm using 3 fit parameters. Otherwise, it will crash. Like if I only use 2 fit parameters in my function and I tell it there are 3, it will crash. So we have to, if you use a, b, and c, make sure you have this set to 3. If you use a, b, c, and d, make sure you have it set to 4. Otherwise it'll crash. And by the way, if we did something like this, c plus d, I hope you guys can recognize as physics professors that if c plus d is supposed to be 1, it could be 0.5 and 0.5 or 0.1 and 0.9, and the computer can't possibly tell which of those it should be. And that will also crash the computer. So you do have to be a little careful in these fit functions to make sure they're reasonable. But as long as you get the right number of fit parameters and you type a function that actually can be fit, you can have any arbitrary function, which is kind of cool. All right, so I am gonna guess some starting values. I think my measurement uncertainty is going to be small, like maybe 0.1 millimeters, and I think my I can use 1 picofarad for my So I'm just giving some values that I think might be close to make the autofit work better. And what we see now is we get a great fit. And of course, on the actual graph, the error bars look really small still, and the curve seems to fit the data really well. But what's more interesting is coming down here and looking at the residuals. And there's 2 important things I want to talk about with the residuals. The first one is these error bars represent a combined x and y uncertainty. So each data point has both uncertainty in the y direction and uncertainty in the x direction, which normally most fitting programs can't really deal with. So the way I do that is I first fit the data equally weighting all the data points, and then I find the slope at each data point. And if I know the slope at each data point, what that will let me do is then take the x uncertainty, multiply by the slope, and convert that into a y uncertainty, an effective y uncertainty. And then I add that in quadrature with the actual y uncertainty to get a total effective uncertainty for each data point. And you can tell that when the slope is really steep, that gives more effective uncertainty than when the slope is really small. These data points down here have less uncertainty overall because when I multiply by that slope, it creates a smaller uncertainty, which is why these data points have a bigger overall effective uncertainty. I hope that makes sense. It's really cool because we're using a weighted fit, and we're weighting the fit based on the total effective uncertainty. We're also calculating the chi-squared based on the total effective uncertainty, which most chi-squared algorithms can't do. I did get all of my math from this textbook. It's a cool little book, but even in the textbook, they assume that all the data only has y uncertainties. So this program's actually doing some pretty sophisticated work. Okay, so a couple of really cool things here. First of all, we get both x and y uncertainties in our data. I plot the residuals with the total effective uncertainties. This is really cool. This data, this is real student data. And what I see in these residuals is that they do look like they're randomly scattered around the curve. And they're all within one error bar, which actually means probably I've overestimated the uncertainties in my data collection, because having all of them be within one error bar is unlikely if the uncertainties are actually random. So I've probably overestimated my uncertainty in the data points. So then we also calculate a chi-squared, and I'm going to be really careful in this video not to try to directly describe how to interpret chi-squared. But basically this is a tool for model testing. If you know the chi-squared and you know the number of degrees of freedom, the degrees of freedom is the data points minus the number of fit parameters we used. So I've got 9 data points. I used A, B, and C. That's 3 fit parameters, so 6 degrees of freedom. If you know the chi-squared and you know the degrees of freedom, you can make statements about whether or not this model is a good fit for our data. So this is a model testing tool, and again, I'll refer to this textbook on how to interpret chi-squared data, but this one, it turns out, the interpretation of having a chi-squared of 1.8 on 6 degrees of freedom is that we've probably overestimated our uncertainties. We would expect that chi-squared to be closer to 6 if the data was truly random and we had correctly interpreted our uncertainties. Anyway, so let's go a little bit further. So this, by the way, I would just do a screen capture of this and put it into a report if I was a student. And I would take the chi-squared and make some well-informed statements about how good the model is at fitting the data. And then also down here, it tells us what the actual fit parameters are. It says the fit parameter A is 0.25799 plus or minus 0.0114. Fit parameter B with an uncertainty, and fit parameter C with an uncertainty. And the fit parameters B and C we can very easily interpret. Remember, B was the systematic error in measuring of the gap. And what we got was 0.6 millimeters plus or minus 0.6 millimeters. So that says there was a very small systematic uncertainty in the gap. In fact, it was consistent with 0. On the other hand, the systematic uncertainty in the capacitance was 2.56 plus or minus 0.17 picofarads, which means that there was a significant systematic measurement error in the measurement of the capacitance of those disks. In fact, basically all the capacitances were we measured were 2.56 picofarads high or 2.56 picofarads low. I forget. I have to think about that for a minute. The last piece of data we have is the actually the most interesting. It is the fit parameter A and its uncertainty. 0.0114, we'll call that. And I wanted to talk about that a little bit, what I do with that with my students. So A was equal to 0.0257799 plus or minus 0.0114. 1, 2, 3, 4. Okay, so we'll call that 80. 0. Is that right? 25780. Like that. 1, 2, 3, 4 digits. Okay. Sorry, trying to make the number of digits in my uncertainty and the number of digits in the, or anyway, trying to make that match. The radius, okay. Anyway, here's the point. That fit parameter, A, is supposed to equal epsilon 0 times pi times the radius of the plates squared. So what that means is we can use the value of A to find epsilon 0. So once the computer tells us what A is, oh, I'm sorry, that's not on your screen. Once the computer tells you what A is, by plugging in the value for A and the value for R, we can find epsilon 0, and R is 0.0889 plus or minus a quarter of a millimeter. So that's in meters. And the units for A are a little bit tricky. We'd have to go back to the equation to figure out exactly what they are. But epsilon 0 has units of picofarads per meter. So it must be that A has units of picofarad meters. Because when I divide by meters squared, I get picofarads per meter. So I think that must be right. Okay, anyway, when I plug in my numbers, I get a value of epsilon 0 that's 10.6. Now we know epsilon 0 is actually 8.85 picofarads per meter, so this is not a perfect measurement by any means. I would love to spend 10 minutes talking about how we figure out the uncertainty in our experimental value of epsilon 0. I use the crank 3 times method, but that's not what this video is about. So I just wanted to say that you can use your fit parameters to do the actual physics, right? That's where some cool stuff happens. So anyway, what's the takeaway? Arbitrary curve fitting, sophisticated chi-squared model testing using both X and Y uncertainty, pretty plots with residuals that make it easier to decide if our model is capturing the physics represented in the data or not. So if you find it useful, I hope you'll use it. And if you don't find it useful, that's okay too.